I audible? Write in chat. Am I audible? Hello. Am I? Okay. तीन चार जण अटेंड करते तर काय लेक्चर घ्यायचं रे? होय. प्रत्येक लेक्चरला असंच असतं का तीन चार जण अटेंड करते? Mobile radio propagation. I have sent you a assignment and you have to write assignment and upload it on the Moodle. I have not prepared complete Moodle, and when I am going to open the space on the Moodle, I probably today I am going to do that, and you have to solve that assignment and make the PDF upload in that particular Moodle section. Okay, so that will be the this thing. In first part, we have discussed about the wireless mobile communication, its technology, changing technologies. What are the different aspect related to the changing technology? And basically, it's a cellular system. And what is the principle of the cellular system? What are the different terminologies related to the cellular system? How splitting of the cell and many more things we have discussed. And related to that, some examples are also there. So you keep in mind that the whatever the equations are there, these are the very we can say elementary equations, and related to that examples will be there, and we can say the any theory questions will be there. Okay, so principally, what is the this thing is you must know, that is cellular system, how it works, that you must know. In mobile radio communication, large scale path loss is the first part, and the small scale path loss is the second part. So, in modeling of these particular path losses is the basic we can say the thing behind the researchers and what are the scientists are there. Okay, so means path loss between the transmitter and receiver, how it can be modulated, or the we can say the mathematically represented. That particular part they did in this particular section. In this particular chapter, we are going to see the mobile radio communication channel places the fundamental limitations of the performance of the wireless communication system. Okay, so wireless transmission path has a line of sight, that is the one thing, and non-line of sight, that is the another thing that we have to keep in mind. And because of the line of sight, the whatever the reception is there, how it affects. If it is, if at all it is not the non I mean, line of sight, then how it is affects that particular part. Means shadow regions are there, and how we are going to cover these particular shadow regions with the different technology. Radio channels are random and time varying. Um, Modeling of the radio channel have been one of the difficult part of the mobile radio design, and done in the statistical manner. So, a radio channel allocation or the modeling, we can say, that is difficult, and it is they are going to do in the different way. It's a dynamically, also it's a statically. When the electrons move, they create EM waves, and that can propagate through the space. By using the antennas, we can transmit and receive these EM waves. Microwave, infrared, visible light, and the radio waves can be used. So, what are the different, we can say, the different types of the waves that can be used? That is the microwave. Above 1 gigahertz are the microwaves, we can say infrared, uh, um, infrared, visible light, and the radio waves that can be used for the transmission purpose. Uh, from this particular side, what we can keep in mind, that is one thing is the in wireless or the mobile communication, we know that the line of sight is one of the things where the transmitter and receiver are in reach directly, and there is no any obstacle, means solid obstacle in between. Okay, so that is nothing but line of sight. Non-line of sight, there is a solid obstacle between the transmitter and receiver, that we can say the non-line of sight. In case of the line of sight, we can say there are no much more hurdles to transmit the signal, and we know that the whatever the radio frequencies are there, some part of the radio frequency uses only the line of sight communication. As usual, we know that the FM uses the line of sight communication. But if you are moving towards the lower frequencies, which are used for the AM commercial applications, in that particular case, what happens? They are not any constraint related to the line of sight communication. Okay, so that is the thing we have to keep in mind, and it uses the skywave communication, it uses the ionospheric communication, and that's why it is possible to transmit the signal in case of the, we can say, radio signals which are comes under the commercial AM band. So we know that the radio channels are random, and it is specified with the some institutions which are at the a higher level, and with the help of that only these channels are allocated. As we know, that means 500 kilohertz to 1640 kilohertz is the channel allocated for the AM commercial applications. 88 megahertz to 108 megahertz is the channel allocated for the FM commercial applications. 800 to 900 it is for the mobile communication. 1800 to 1900 it is for the mobile communication. 2.1 gigahertz it is for the mobile communication. As usual, the 2.4 gigahertz and 2.5 gigahertz in that particular channels also. The sub channels are allocated for the mobile communication also. In case of the moduling, means how the signal is going to reach out at the receiver side, and what are the different things we have to keep in mind, and how the attenuation of signal is taking place. That particular part is nothing but the modeling of the radio channel, and that is in terms of the large scales we will discuss in this particular lecture. When the AMUs is means any antenna is going to radiate the signal, and these radiated signals are EMUs. Okay, so some radiation properties of the antenna comes in picture, and how these particular signals are transmitted in the environment, or we can say the towards the receiver. Okay. Also means microwaves has its own we can say properties, according to they are going to work. Infrared has its own properties, and another radios which are used for the communication purpose, these are also having, means each and every band of frequencies has its own different properties, and accordingly they are working or behaving in the medium, and that particular part we have to keep in mind why moduling the radio channels. This is the very important part, we can say, in this. Now, properties of the radios. Radios are easy to generate. We can say that we can have antenna which has the input, which is the electrical signal, and antenna is going to radiate the signal. It can travel long distance, as we know that particular thing is very important, and they are going to travel long distance according to the whatever the power content in that particular waves. Can penetrate building, and as usual we know that mobile means we have a mobile. We cannot see the base station if we are in the building, and then also we can receive the signals, and that is nothing but they are penetrating through the building, that is walls or floor, or we can say the any type of the roof, and that's why it is possible to receive the signal in the building, we can say, may be used for both indoor and outdoor coverage. um, are omnidirectional, can travel in all directions. This part is very important, and as we know that this omnidirectional can travel in all directions. As usual, we know that we have gone through the antennas, that is which are not in one direction it is omnidirectional, another direction they are directional, more directional we can say. Uh, can be narrowly focused at high frequencies greater than 100 gigahertz, 100 megahertz using the parabolic antennas. Sir, with these particular properties, one can transmit the signal as usual. How the requirements is there, and they are going to receive it. Means many times means we know that some of the frequencies are having the properties of the light and accumulation with the help of the parabolic reflector. They may be possible. Okay. आता प्रोपोगेशन मॉडेलकडे जायचं आहे आणि प्रोपोगेशन मॉडेल काय सांगते तर लार्ज प्रोपोगेशन मॉडेलमध्ये व्हॉट एव्हर द थिंग्स दे हॅव डिसाइडेड दॅट इज द प्रेडिक्ट mean signal strength for an arbitrary transmitter, mean signal strength for the arbitrary transmitter receiver separation, estimate radio coverage of the transmitter, estimate radio coverage of the transmitter, characterize signal strength over a large transmitter receiver separation distance, several hundreds and thousands meters. This is characterize signal strength over several transmitter receiver separation distance, hundreds and thousand meters. स्मॉल स्केल साठी काय काय आहे तर स्मॉल स्केल साठी आहे कॅरेक्टराइज रॅपिड फ्लक्च्युएशन, रिसोर्स सिग्नल स्ट्रेंथ और व्हेरी शॉर्ट ट्रॅव्हल डिस्टन्स, short time duration, order of the seconds, and a few wavelengths, very short travel distance and the short time duration. 11 वाजता. Free space propagation model has the properties like we have to take into consideration for the LOS. LOS between transmitter and receiver. Example is the satellite and the micro communication is there. In that cases, these things are comes in picture. As usual, we have discussed about the Friis formula in the first chapter of the antenna and wave propagation, and accordingly, Friis formula says us about the power received divided by power transmitted is equal to um, effective aperture of the transmitting antenna into effective aperture of the receiving antenna divided by r square into lambda square. This is the equation we have discussed in case of the Friis formula. Means effective aperture comes in picture here. We have converted that effective aperture into the gain of the antenna, that is transmitting gain of the antenna and the receiving gain of the antenna, and it uses this particular equation G is equal to 4 pi AE divided by lambda square. Okay, so L is the here L is given that the R is nothing but the distance between the transmitter and receiver. Here we are going to take that particular D is the distance between the transmitter and receiver. L is the loss factor. Loss factor is one of the added thing in this particular free space propagation model. That is, L is greater than 1 indicates loss due to the transmission line attenuation and the filter losses and the antenna losses. L is equal to 1 indicates that no loss in the system hardware. Gain of the antenna is related to the effective aperture of the antenna, and that can be written as Z is equal to 4 pi AE. AE is the effective aperture divided by lambda square is the wavelength of the transmitted signal. Okay. So effective aperture AE is related to the physical size of the antenna. Effective aperture AE is related to the physical size of the antenna. As you know that it depends on the what type of the antenna is, what is the what is the physical aperture of the antenna, and from that we can calculate the effective aperture of the antenna. Lambda is equal to c by f, as we know, and c is the speed of light. Pt and Pr must be in the same units, that is watt or the kilowatt. Gt and Gr are the dimensionless because these are the gain of the antennas. Isotropic radiator and an ideal radiator, which is radiates power with the unity gain uniformly in all directions and is often used as a reference. Isotropic radiator is not the physical radiator, or we can say it is the hypothetical concept only. We have taken presentation. Hello, hello, yes, hello. Am I audible, all of you? Rutuja Khandekar. Am I audible? Okay. Rutuja, are you with me, Rutuja? Hello, Rutuja. Rutuja Khandekar. Hello, Rutuja. Anjali.
Yes, sir.
Hello, Anjali. Okay.
Yes, sir. You are audible.
Akanksha. Akanksha.
Yes, sir.
Okay. Khandekar Rutuja, I think this year started, and Rutuja Khandekar is there. Hello,
Yes,
Rutuja.
sir.
Okay, okay. So, if any measurement we have to do in that particular cases, one thing we have to keep in mind that some hypothetical concepts we have to underline, and with the help of these hypothetical concepts, we are going to write, or the we can say the uh, measure the different parameters of the antenna. Effective isotropic radiated power, that is EIRP, is equal to PT into GT. So um, represents the maximum radiated power available from the transmitter in the direction of the maximum antenna gain as compared to the isotropic radiator. It is like the directivity, whatever we have discussed about in the antennas. Okay, so that we have to keep in mind. So प्रिस्पेस मॉडेल मध्ये काय काय येतं, तर एक येतं फ्रीज फॉर्म्युला. फ्रीज फॉर्म्युला लक्षात ठेवणं फार सोपं आहे. PT PR divided by PT is equal to AET into AER divided by lambda square into R square. R square is the distance between the transmitter and receiver. That is one thing. That is denoted in this particular case. It is by D. Second thing we have to keep in mind that AET and AER are also represented in terms of the gain of the antenna, and that is with the help of the equation, that is gain of the antenna is equal to 4 pi into effective aperture divided by lambda square. So effective aperture one can replace with the help of the AET is equal to GT lambda square divided by 4 pi, and AER is equal to GR lambda square divided by 4 pi. And that particular things, if we put in that equation, we'll get this equation. Okay. And one more parameter here added, and that particular parameter is the L. Okay. So, where this particular L is the loss factor we have to add. Loss factor is greater than 1, increases the losses of the transmission line attenuation, filter losses, and antenna losses. Indicates one no loss in the system hardware. So that is the thing we have to keep in mind. In practice, effective radiated power ERP is used instead of the EIRP. Effective radiated power is radiated power compared to the half wave dipole length, dipole antennas. Half wave dipole antenna is nothing but lambda by 2 is the size of the antenna, as compared to means lambda is the wavelength. Since the dipole antenna has the gain of 1.64, that is 2.15 dB, ERP is equal to EIRP minus 2.15 dB. ERP will be 2.15 dB smaller than the EIRP for same transmission medium. So what terminology we are going to normally use, that is the effective radiated power, rather than EIRP, that is the effective isotropic radiated power. Okay. Uh, and simple dipole, in case of the since dipole antenna, we have to calculate the gain, and how that one can be calculated, that is the ERP is equal to EIRP minus 2.15 dB. Now we are moving towards the calculation of the path loss, and main important, or the main thing we are going to calculate is the path loss only. Represent the signal attenuation and is defined as a difference between the effective transmitted power and the received power. So path loss PL in dB is equal to 10 log PT divided by PR. It is how much is the transmitted power is there, and how much is the received power at the receiver side. Okay, so it is one can calculate it is by 10 log PT divided by PR is nothing but whatever the equation of the what we can say the Friis formula, and we can add it. Now Friis formula is PR divided by PT, and that's why what they did, that is minus 10 log GTGR lambda square divided by 4 pi into 2D square. Okay, for 4 pi square into d square. This is the equation we can write in terms of the logarithmic for the path loss in dB. Without antenna gain, with the unit antenna gain, antenna gain gains, PL can be calculated. म्हणजे antenna gain 1 असेल तर काय आपण इक्वेशन लिहू शकतो, तर -10 GTGR goes to 1 and lambda square divided by 4 pi square d square. Friis free space module is valid predictable for PR for values of the D which are in the far field of the transmitting medium. आपल्याला माहित आहे फार फील्ड काय आहे, नियर फील्ड काय आहे अँटेनाचं, आणि त्याच्यानुसार हॅलो करिश्मा, हॅलो करिश्मा, हॅलो, अरे बोल की, आर यू विथ मी करिश्मा, प्रियांका?
Yes, sir.
Okay, Priyanka, you joined now only?
Yes, sir.
Okay, why did so?
सर मगाशी जॉईन झालेले नेटवर्क प्रॉब्लेम मुळे परत रिजॉईन केला.
Okay, okay, okay. Karisma, are you with me, Karisma? Hello? Hello? Karisma? You called me yesterday, Karisma. Hello? For the Byju's, I am going to send a link. You have to register on the link for the Byju's, and then we will decide that where will be the placement campus. Okay? Okay. Sir, whatever we have discussed about, or whatever we have discussed about, based on the Friis formula. If you are going to write well Friis formula and related to that the equations, we can manipulate all the equations according to the requirement, and we can calculate the path loss, and as usual, path loss is the ratio of power transmitted divided by the power received. Okay. And one can calculate this. One thing we have to keep in mind, that whatever the calculations are of the power is there, these are in the far field only. The far field or the Fraunhofer zone that is beyond d 2d square by lambda, that is dm given as d is the largest physical linear dimension of the transmitter antenna. Additionally, df is greater than capital D and df is, that is whatever the distance must be greater than the lambda. Free, free space equation does not hold for d is equal to 0. Large scale propagation models use the close-in distance d naught received power reference point chosen such that d naught is greater than or equal to 2f. Received power in free space at the distance greater than do, that is PR for the d distance, PR d naught divided into PR into d naught divided by d square, and d is in between the df and d naught. PR with the reference to 1 milliwatt is represented as, that is 0.01 only. In the denominator they are going to add plus 20 log d naught divided by d. Electrostatic, inductive, and the radiated fields are launched due to the flow of current from the antenna. Region far away for the transmitter, electrostatic and the inductive fields become negligible. The radiated field components are considered. On this particular slide, whatever the given is relative to the far field antenna of far field of the antenna. In near field, what can one do for the reception of the power? Normally, we know that in the near field there is no reception of the power, and for the we can say scientific calculations they made, and accordingly that they have shown the what they are going to do in this. Okay, so this is the main thing from this particular slide. That is always we must means if you have to calculate the path loss in terms of the freeze formula, and then we have to keep that antenna in the far field only. One equation, one example they have given, that is what will be the far field distance for the base station antenna with largest dimension d is equal to 0.5 meter. And the frequency of operation is fc is equal to 900 megahertz and 1800 megahertz. So you write in your notebook and calculate this particular, that is d is equal to 2d square by lambda. Distance small d is equal to capital D square by 2 into capital D square in divided by lambda, where capital D is the 0.5 meter and frequency of operation is 900 megahertz and 118 megahertz. So you do calculate this particular part and tell me. Anjali? Hello, Anjali. Akanksha? Madhuri? Priyanka?
सर
हाँ, 900चा लॅमडा कॅल्क्युलेट करा, 1800चा लॅमडा कॅल्क्युलेट करा. स्मॉल डी इज इक्वल टू 2d स्क्वेअर बाय लॅमडा हे लिहायचं आहे आणि ते कॅल्क्युलेट करून चॅट मध्ये टाका. टाकू शकताय? सगळेजण करा. माधुरी, आर यू विथ मी?
यस सर
Okay, can you calculate this?
यस
It is
सर
very simple. Okay, do calculate. Do calculate, all of you. Here they have given the answer. Okay. So lambda is equal to this one and df is equal to this one. For first part, where the lambda for the 900 megahertz and 1800 you can calculate it. 1.5 meter is the it is the near field boundary only, and out of this particular boundary there is a far field. Uh, Nearer to this particular boundary there is the near. Example 2, if the transmitter produces 50 watt power, expresses the transmitter power in units of A, dBm and dB watt. If 50 watt is applied to unity gain antenna with 900 megahertz carrier frequency, find the received power in dBm at free space distance of the 100 meter from the antenna. What is the PR? Assume unity gain for the receiving antenna. काय सांगितले बघा, if the transmitter produces 50 watt power, express transmitted power in the dBm किंवा dBW. कशामध्ये dBm means dBW कशामध्ये हे करा आणि लॉस काढा म्हणून सांगितले आणि रिसिव्ड पॉवर किती असेल ती कॅल्क्युलेट करा म्हणून सांगितले. ट्रान्समिटेड पॉवर एवढी आहे तर रिसिव्ड पॉवर किती असेल. They have given the frequency and that's why we know the lambda. They have given the distance, that is 10 kilometer. Space distance is the 100 meter from the antenna and that particular part also one can calculate. म्हणजे त्याच्यावर आपण सगळं ते calculate आणि युनिटी गेन आहे ते, त्यामुळे काय प्रॉब्लेम नाही. कॅरियर आहे 900 मेगाहर्ट्ज 50 वॅट पॉवर हे केलेले आहे. ट्रान्समिटर पॉवर PT इन dBm, PT इन milliwatt divided by 1 milliwatt, that is 47 dBm power APP. Transmitter power is PT is equal to, in watts it is 17 dB. Now transmit received power can be determined by using PR is equal to PT GT GR lambda square divided by 4 pi square D square L square D square L. Okay, now gain are 1, GT and GR gain are 1. 50 is the power. 1 by 3 is the lambda, whatever calculated for the 900 megahertz. 4 pi square into the 100 is the distance between the transmitter and receiver, and loss is 1. They have considered, and that's why 3.5 into 10 raised to minus 3 milliwatt is the power received. PR in dBm one can calculate, that is minus 24.5 dBm. And the received power at 10 kilometer also one can calculate, that is only the distance D is 10 kilometer, and one can do that particular also. So this is based on the Friis formula. Friis formula is the very simple formula we can say, and with the help of that the manipulation related to this is the only the whatever the distance is there, lambda is there, and the loss and the PRMB. So these are the terminologies used in the Friis formula for calculation of the loss, as well as we can say the calculation of the power received. Propagation mechanism काय असतो तो बघायचा आपल्याला. As we know, that means propagation through the medium is taking place, but whenever the obstacle is there, what will happen? So three basic propagation mechanisms will which impact the propagation in the mobile radio communication system. As we know that in case of the any wall is there and we are going to transmit the signal, what happens? It is reflected back, diffracted, it is reflected, diffracted, and the scattered. Okay, so these three possible, we can say the um, uh, uh, possible way the electromagnetic wave may propagate towards the receiver. That is the thing we have. Reflection is nothing but completely reflection of the waves from that obstacle. Diffraction is nothing but whatever the waves are there, we are the diffracted, passed through, means whatever the energy content in that particular goes on reducing, but they are going to pass through that particular part. And the scattered is nothing but the because of whatever the area is there, what is the type of area, accordingly the scattering will be. Propagation mechanism is the reflection occurs when the propagating electromagnetic waves impinging on the object which has a very large dimension and as compared to the wavelength. म्हणजे wall आहे समजा, एखादी building आहे, एखादं tree is there. So surface of the earth, buildings, walls. Diffraction occurs when the radio path between the transmitter and the receiver is obstructed at surface has a sharp irregularities. Sharp irregularity explains how radio signal can travel urban in the rural environment without a line of sight. विदाउट लाईन ऑफ साईट पाथ मध्ये ह्या सगळ्या गोष्टी होतात. आणखीन ते आपल्याला लक्षात ठेवायला पाहिजे. सर स्कॅटरिंग ऑकर्स वेन द मीडियम हॅज ऑब्जेक्ट दॅट द स्मॉलर ॲज कम्पेअर टू द वेवलेंथ. वेवलेंथपेक्षा स्मॉलर ऑब्जेक्ट आहे त्यावेळी स्कॅटरिंग होते. स्मॉल ऑब्जेक्ट इरेग्युलरिटीज ऑफ द ऑन द चॅनल अँड द स्ट्रीट साइन्स, foliage, street signs are there. In that particular case, the scattering happens. Reflection occurs when the radio is propagating in the medium, impinging upon the another medium having a different electrical properties. Like wall, we can say if the radio wave is incident on a perfect dielectric, part of the energy is reflected back, part of the energy is transmitted. That is the thing we have to keep in mind. In addition to the change in direction, the interaction between the wave and the boundary. In addition to the change of the direction, interaction between the wave and the boundary causes the energy to be split between the reflected and the transmitted waves. Okay, so amplitudes of the reflected and the transmitted waves are given relative to the incident wave amplitude by Fresnel reflection coefficients. तर हे बेसिक थिंग आहे. डिफ्रॅक्शन कुठं होतं, शार्प एजेस असतील तिथं होतं. स्कॅटरिंग कुठं होतं तर स्मॉल ऑब्जेक्ट्स आहेत ॲज कम्पेअर टू द वेवलेंथ ते असतील तर होतं. आणि रिफ्लेक्शन कुठं होतं तर मोठे ऑब्जेक्ट्स आहेत त्याच्यामधून रिफ्रॅक्ट पण होते वेव्स आणि रिफ्लेक्ट पण. Reflection when the radio is propagating in one medium, impinging on another medium, having the different electrical properties. The wave is partially reflected and partially transmitted. आता हे पोलरायझेशन आहे, हा पार्ट आहे. रिफ्लेक्शन डायरेक्शन्स आहे, त्याच्यानंतर रिफ्लेक्शन आहे. These are the things which are we can say somehow we have connected with these with the different subjects, and that's why we have to miss ground reflection ray module also we have discussed in case of the space wave communication. These particular things we have calculated all the things. These are also we have calculated phase difference and path difference. So these are the things you go through these PPTs. I'm going to share with you the PPTs, and we will meet in the tomorrow's lecture and go through this particular whatever the things are there. We have gone through this, or we can say we learned this particular part. That's why it is not much complicated to understand. That is the one thing, because you are interfacing it with the toys, and you go through these particular PPTs, and we can say get more information related to this part. Okay, so we'll stop here, and we'll